Today we're going to get into the really big idea. So, what do we really need from studying electrostatics? And it's this idea of electric potential. So, just because there's an electric force that can displace anything that is charged, so that's just saying it moves it to somewhere else, it's capable of doing work. Any force is capable of doing work. So the presence of some electric field tells us that, hey, this charge is able, it has the potential to do work on other charged objects. And in studying the electric potential between two different points in a field, we can learn a lot about the work that could be done and energy that's associated with that force moving charges around two other points. Since we've been drawing all these analogies to gravitational forces and how electric forces are somewhat similar to that, and that they're field forces and blah blah blah, all the stuff we've said before, we can still draw another analogy here. So let's say you have a bookshelf. On the bottom shelf, you have your physics book. So if you take that physics book off the bottom shelf and move it to the top shelf, if we're talking about gravitational forces, then you've increased its gravitational potential energy. You've moved it to a higher distance above the Earth's surface, so you increase the gravitational potential. So in that respect, it's very dependent on location. It's very similar in electrical potential energy. So because you have an electric field exerting a force on any charge that comes into its field, and because that force is going to cause the charge to move a certain distance, whether it's positive or negative, then we can say that electric field is doing work on the charges. So remember, work is when some force causes something to move. So a charge in an electric field has some potential energy U. Just be careful with that, because in the last unit we called that total internal energy. Here U is going to represent a potential energy. So just like when we were doing the thermal physics unit, potential energy of a charge is going to decrease if work is done on it. So that might get a little confusing with the analogy we drew earlier. If you're doing the work, you're increasing the book's potential energy. But since it's gravitational potential energy that we're talking about, if gravity does work on it, so the force due to gravity causes it to move from the high shelf to some point that's lower, then we would say that gravity has done work. The overall potential energy of the book has changed. So that's why we're saying here the electric potential energy of a charge is going to decrease if some electric force does work on it. So in equation form, that would look like delta U, so change in potential energy, is equal to negative work done on the charge. Alright, so we know now that however much the potential energy changes is equal to the opposite of the work that was done on it, but how are we actually going to calculate that work? The work done to move any charge is just the same as it was before. It's the force F that was exerted on the charge, and we're going to multiply that by its displacement d. So however far that force caused it to move. So keep in mind, it's got to be in the direction of the force. So whatever displacement went along with the force. We set up a couple equations in previous videos to talk about the force. So magnitude of the force exerted on some charge Q in some electric field E was just F sub Q equals Q times E. The force on our charge Q is equal to however big our Q is multiplied by the electric field that it's in. So we can come up with this equation to figure out how much work is done on a charge. So we know work is force times distance. And up here we said force is just charge times the electric field times the displacement. If you are exceptionally clever, you might be thinking right now, well, the force and the electric field, those both depend on how far away you are from the charge, right? So if you get a little bit further away, the force drops, the electric field drops. So what's going on there? And really the answer to that is, what did I save it as? There we go. In real life, real physics, we would be looking at this integral. So the force would be some function of distance, and you would integrate according to that. But since AP Physics 2 is just algebra based, we don't have to worry about doing this integral. Whenever we work with a force or an electric field, we'll be dealing with it like it is a constant value. So we do not need to worry about integrals here. Keep in mind too, when you're working through these problems, that this distance or displacement that the charge is being moved through is not just its overall displacement. We take only the part that goes along with the force. So we'll look at some examples here down below. So first little sub-point to that. When you have a charge that moves a distance, we'll call it r, moves a distance r parallel to the electric field lines, then it's pretty simple to calculate the work because the whole distance is parallel to those electric field lines. The force has caused all of the movement. So we could just say that QED, if it moves a distance r, we plug r in for d, and we could just say work done is Q times E times r. So that's this picture here. Our charge Q is in some uniform electric field, so it has a constant value. We don't have to worry about integrals. That electric field, remember, it shows which way that a positive charge would want to be moved. Since our Q looks positive, then it's going to move with the electric field lines. This R goes in the direction of the electric field lines. So work it done is just Q times E times R. The second picture though, what is going on there? When the charge moves a distance r that's perpendicular to the electric field lines, then what is the work there? So here's our positive charge Q. It's moved a distance r this way. But since our Q is positive, the electric field is positive, the field should want to push it this way. It should want to go with the field. But that's not what happened here. So in moving from its original position to r, the force had nothing to do with that. So that force did zero work. And then the third picture here. When the charge moves some distance r at an angle theta. Hold on one sec, I gotta copy my. So the charge moves a distance r at an angle theta to the electric field lines. Then the work done is equal to, let's see here. Okay, our Q starts out here. It's moved a distance r at some angle away from being parallel to the electric field lines. So we need to look at, we don't really care about the sideways distance. We only want to know what is parallel to the electric field. So that just sets up a right triangle here. So we have this line, and we have this line. In moving from its original position to r, it's moved up some, and it's moved to the left some. Since we said in step 2, we don't really care about the horizontal stuff because that's just 0. Then we only care here about this parallel part, the part that goes with the field. So that's going to be like step 1. But we can't just call it QER. We have to figure out what component of R goes along with the field. So to do that, since that side is adjacent to the angle, and R is the hypotenuse, we would have Q times E, and then to get that vertical component, we would use R cosine theta. Q times E times R times cosine theta. Just to show that calculating work done just like it was before is completely path independent. So we take this Q, it goes all crazy, and finally we stop looking right here at the tip of the arrow. So Q effectively has moved from this point up to this point. We look at the overall displacement, don't care at all about the path. So you can see from here that it has moved a vertical distance d. This d represents from where it started, only the vertical distance up to where it finished. So work there would be Q times E times D. Example time. We have this electric field E. So all of these arrows that emanate from this center charge represent the electric field E. This E is being generated by that pretty large central positive charge. We take another positive charge Q, it's not in the picture here, but we're moving it in the circular path shown. So it starts here at A, we take it along the path over to B, and then we bring it in from B to C. We want to figure out how much work is done by the electric field on the charge. And then we want to say if the charge was then made to return in a straight line from C to A, how much work would be done? So let's look at this first part. How much work is done moving the charge from A to B to C? Alright, well let's look first at A to B. So first we want to figure out what is the work done moving from A to B. So let's check out this picture. From A we come around, we hit the first electric field line at a 90-degree angle. So we're moving perpendicular to that first one. We do the same thing to the second. At the instant where we cross over that electric field vector, we're crossing perpendicular. same one here, also perpendicular. So really from A to B, the radius of this kind of circular path that we're taking hasn't changed. A is as far away from the center as B is. So from that, we could say that this giant charge that is generating this electric field has done no work in moving from A to B. We haven't moved out away from the charge at all, and we haven't moved in closer to the charge at all. So the work from A to B would just be 0. Alright, for B to C though, let's see. So from B, we come straight in toward the center charge, a distance r towards C. So that means all of the work is going against the field. Since we have a positive charge, we're going against the field lines. So work from B to C would be equal to our positive charge Q multiplied by the electric field that it's in, E. We bring it in a distance r. R is completely, I guess I can't say parallel to. What can we say? Okay, maybe we can say parallel to. Let me add in one more electric field vector. So this vector I just added in is just another electric field vector. It comes straight out from the charge. So you can see that now from B to C we are completely parallel to that electric field. So all of the work done there is due to the charge. So we don't have to worry about any cosines or anything like that. So let's jump back down here. So it's Q times E times R. But we've gone in the opposite direction that that electric field would want to make the charge go. So that work we've done is actually... Seriously, I can't put in a negative sign? We'll cheat the system here. There we go. So the work that we've done is actually negative QER. Instead of decreasing our charge's energy, we're actually increasing its potential energy. We've brought it from farther away from a similar charge, and now at the end it's closer to a similar charge. So that repelling force is going to be a lot stronger. We've stored a lot more energy in there. The next part of this question was how much work is done to move the charge from C right back to A. Let's take a look at this picture again. So we want to go from C directly back to A. Well, that's going to be kind of goofy. We have some kind of angle. We cross over at this weird path. We're not parallel. We're not perpendicular. It seems almost like we don't have enough information to answer it. But you have to remember that we said from A to B that electric field did no work. So that means whatever the potential is at A, it would have to be the same as the potential at B. So if from B to C, we said that the work done is negative QER, well then going from C to A would essentially be the same as going from C to B. So we're just doing the opposite work. So the work from C to A would be exactly the same as the work going from C to B, which would just be the opposite of this. So what's opposite negative QER? Positive QER. Gravitational potential energy, that there's not really any certain point that we have to measure it from. And in the same way, we don't have to do that with electrical potential energy either. There's no certain zero, there's no certain value of 100 joules, anything like that. What we really care about when we're talking about potential is how much different it is from one location compared to another. So we care about in electric potential the potential difference, and that variable for potential difference is V. So we'll talk about V a lot in this unit and the next unit. So we care about potential difference between 2 points. So one place you may have seen this V a lot, potential difference or voltage, may be a little more common. The voltage reading on a battery, also its potential difference reading, tells us how much energy difference there is between the positive end and the negative end of batteries. So that tells us how much energy we could actually get out of it by letting electrons move from one end to the other end, just from their natural electric charges. But batteries will come into play more so in the next unit. So potential difference, all we need to know right now is just a measure of how much work we can get out depending on how much charge. And we measure it in joules per coulomb. So in equation form, it would look like V, potential difference, is equal to work divided by charge. So you can see there when we plug into this equation, V would be equal to, how do we measure work? That's a joule. How do we measure charge? That's a coulomb. So you may run into joules per coulomb way more often. You will see that called the volt. So 1 volt equals 1 joule.